So this is question 6 from the year May 2025, paper 2 CR. So let's just solve this. Okay. It says that a student does titration to find the volume of a student does titration to find the volume of phosphoric acid solution. Okay. Needed to neutralize a sample of potassium hydroxide solution. So they are basically carrying out the process of titration to figure out the volume of phosphoric acid that is needed to react with this potassium hydroxide, acid base reaction in short. Okay, so one of the product of the reaction is potassium phosphate, acid plus base, salt plus water. The student method is this: use a measuring cylinder to transfer 25 centimeter cube of potassium hydroxide solution to a conical flask. Okay, add 2 drops of an indicator. Now they haven't explicitly mentioned what indicator we should be using. Fill the burette with phosphoric acid, okay, and record the initial reading of the burette. Add acid to the conical flask and record the final volume of the burette reading when the indicator changes color. The equation for the reaction is this, okay? So explain 2 improvements with the student method that would give more accurate result. Okay. So first of all, what they're doing is basically let's just try to visualize the overall process, okay? So this is the burette. And in the burette, there's this phosphoric acid. Right? And there's this conical flask. Extremely sorry. I'm bad with me. Just a moment. How do you even draw this? Just I'm bad with my drawings. Excuse me for that. Okay. It may look like volumetric flask initially, but this isn't. You get the idea, right? This is the conical flask. Okay. Sorry for the drawing. This is the conical flask. This is the conical flask where we have the alkali. Okay. We have the alkali over here. That is potassium hydroxide. So how have we transferred the specific volume of alkali in this flask? We have basically used a measuring cylinder. Okay. Now instead of measuring cylinder, what you could do is you could use a pipette to make the volume more accurate. Okay. First thing is that explain 2 results. Okay. First thing. And what can you say about second stuff? Measuring cylinder initial indicator changes color. Um, they're basically adding acid to the conical flask. They are basically adding acid to the conical flask. They aren't basically doing anything, right? They aren't basically stirring or swirling the flask, okay? So yeah, this could be another point. They are basically adding the acid, just they are continuously keep on adding the acid, right? So you cannot do the process in this way. So once you have it, what you have to do is you have to shake this entire thing, right? You have to shake this flask, you have to swirl this around, okay? So why do you even do this, right? To ensure that both the acid and the alkali are fully mixed together or they reacted. Okay, you have to swirl it while you are adding this acid. Okay, so this is basically the overall process that they are carrying out. And obviously there is an indicator over here, and near the end point the indicator is going to change color. Okay, so let's just say methyl orange as the indicator. Okay, so they haven't explicitly said about the indicator, right? So methyl orange, methyl, just a moment. Now let's just say the indicator is methyl orange. Now the methyl orange is in what? The methyl orange is in this alkali, right? In alkali, in alkali, the methyl orange, the color of the indicator in alkali is gonna be yellow. What? The color of the indicator, methyl orange indicator in alkali is gonna be yellow, right? Now, when you are adding this acid, this alkali is getting used up, right? And at one point of time, all of these would get used up, right? So any further drop of acid over here would make what? Would make the conditions in this conical flask acidic, right? So after all of the alkali has been used up, any further addition of this acid from the burette would make the conditions over here acidic, right? And in acidic condition, just a moment, give me a moment to explain. And in acidic condition, the color of the indicator is red, is red. Okay, methyl orange is red, alkaline yellow, acidic red. Okay, now when the color of this turns red, we can be sure that all of the acid has been, sorry, when the color of the indicator is red, we could be sure that all of the potassium hydroxide has been used up. Okay, so yeah, this was the overall process of how do we carry out the process of titration in our syllabus. So yeah, let's just now write the improvements. So first is that use a pipette, use a pipette. Use a pipette so that the volume reading, so the volume of alkali added is precise, so that the volume of alkali added is precise. Right, first thing. And second is that swallow the flask, we swirl the flask around so that the acid and alkali are fully mixed together. So that the acid and alkali are fully mixed together. Mixed together. Okay, so yeah, moving on. It says that um, it says that the student repeats the titration correctly. The potassium hydroxide solution has a concentration of this. The potassium hydroxide solution has a concentration of this. Okay. The phosphoric acid solution has a concentration of this. Okay. Calculate the volume in centimeter cube of phosphoric acid. We have to figure out the volume of the acid needed to neutralize this volume and this concentration of potassium hydroxide solution. You have to make sure that the answer is in three significant figure. Easy stuff. what would be the moles of it? Since this is an aqueous solution, the moles would be volume times concentration. If you have the moles of it, you could easily figure out the moles of it. How? By molar ratio. And if you have the mole of it, you could easily figure out the volume. Why? Because you know that number of moles equals to volume times concentration. You have the moles of this and you have the concentration of this. So you could make volume the subject and easily figure it out. Okay, easy question, easy mark. So let's just solve this. So n of potassium hydroxide is going to be equals to volume times concentration. This should be equivalent to, the volume is what? The volume is 25 centimeter cube, right? Now you have to convert that volume to dm cube. So 25 divided by 1000. Now why are we doing this? Because our concentration is in mole per dm cube. So you have to ensure that the units are the same. Times 0.150. Right? So this is coming as 3.75 into 10 to the power minus 3 mole. Now compare the molar ratio. So it is basically in a ratio of 3 to 1, right? So 3 moles reacts with what? 1 mole of acid. So basically 1 mole of KOH would react with 1 by 3. Therefore, 3.75 into 10 to the power minus 3. Would react with times 3.75 into 10 to the power minus 3. So this should give you a value of 1.25 times 10 to the power minus 3, right? Now this is what? This is basically the moles of phosphoric acid. Now you have the moles of phosphoric acid as well, right? So what? You know that N of H3PO4 should be equivalent to volume times concentration. You have the moles, you have the concentration, you could easily figure out the volume, right? So yeah, put all of this into this. So moles 1.25 times 10 to the power minus 3 equals to volume times concentration is given 0.0400, 0.0400. You make volume the subject, and this should be equivalent to 1.25 into 10 to the power minus 3, 1.25 times 10 to the power minus 3 divided by 0.0400, 0.0400. Now this is coming as 0.0400. This is, just a moment. Okay, now this is coming as 0.03125 dm cube, right? But the thing is that they have basically asked us to figure out this answer in cm cube, right? So to convert dm cube into cm cube, what you have to do is you have to multiply this thing by 1000. Hence, this is coming as 31.25 centimeter cube, but in the answer question they have said us in three significant figures. So basically this, right? So this should be 31.3 centimeter cube. 31.3 cm cube, and hence this is basically our answer to this question in three significant figures, obviously. 31.3. Okay, so moving on to part C of this question, it says that potassium phosphate solution reacts with calcium chloride solution. One of the product is an insoluble solid of calcium phosphate. Okay, so complete the reaction equation. Okay. So how many calcium is over here? 3, right? So there should be 3 calcium over here as well. Now, how many potassium is over here? 6. So there should be 6 potassium over here as well. So 6. Easy balancing. Okay. Now, the student reacts the student reacts a solution containing this mole of potassium phosphate with an excess of calcium chloride. Okay. We have the moles of it, right? Understood. And this is excess. So in any further calculation, we're basically going to use the moles of the one that is limiting, right? Limiting. We're going to use the moles of it for figuring out the moles of other substances. The one that is in excess, we are obviously not going to use it, okay? So when you're having multiple moles, okay, you're going to use the moles of the compound that is in limiting. So for this, it is in limiting. Hence, we are going to use this mole to figure out the moles of other compounds, okay? Now the student obtains these of calcium phosphate. Okay. These of calcium phosphate. So you have to figure out the percentage yield, right? Percentage yield. So that the percentage yield, okay, is 90%, is about 90%. Okay. So to figure out this thing, you basically have to first of all know that formula of percentage yield. So the percentage of percentage yield is actual by theoretical, actual yield by theoretical yield times 100. So using this formula, you'd get the percentage yield of something, okay? Now, actual yield is the one that is always given in the question. Theoretical yield is the one that you have to find, okay? Theoretical yield basically means the mass of something, okay? You have the moles of it. But yeah, you have the moles of it. You could easily figure out the moles of it. And if you have the moles of it, what you could then do is number of moles mass by mR. You have number of moles, you have the mR. So you could figure out the mass of it, okay? And once you have the mass of it, that is the theory mass. You have the actual mass given in the question and you multiply it with 100. And basically, this is how you are going to get the percentage yield, okay? So let's just solve this. The number of moles for calcium phosphate. N of Ca3PO42. So how do you even figure this out, right? So molar ratio concept again. 2 moles reacting with 1 mole. So 2 moles reacting with 1 mole of calcium phosphate. PO4. 2 mole of what? 2 mole of K3PO4. Sorry. K3, 2 mole 2 mole of A3PO4 reacts with 1 mole of calcium phosphate, right? So 1 mole of this times 1 mole of this will basically lead to the formation of 1 by 2 the moles of this, right? So therefore 0.0400 0.0400 would react with 1 by 2 times 0.0400. So this should be giving you around times 0.0400. This should give you 0.02 moles. Now this is the mole of what? This is basically the mole of Ca3PO42. This is basically the moles of you have the moles of it, right? Now what you could do is number of moles of it. So number of Ca3PO4 2 is gonna be equals to what? Mass by molar mass. You know the number of moles, 0.02. You know the AMR that is given in the question, 310. You could easily figure out the mass from here, right? Therefore, the mass is 310 times 0.02. So the mass is 0.004 grams. Extremely small, 0.004 grams. Okay, this is the mass. This is the theoretical mass of it. Okay, so now what you're going to do is you're going to plug all of the values into the formula. That is actual 5.70 and theory is what? Theory is, just a second, did I make any mistake? Just a second. 0. Times 0.0400, right? This is 0.02, okay? 0.02 times 10, 0.0. Oh, sorry, this is gonna be 6.2. Sorry for that. Uh, this is gonna be 6.2 grams. Theoretical mass, right? So 5.70 divided by 6.2 times 100. So this should give you a value of 5.7 divided by answer times 100, 91.9%. Okay, 91.9%. Now this is approximately about 90%. Okay, so this is basically the answer. Shown. Moving on to the last part of this question. So describe how the student can obtain pure dry sample of calcium phosphate from the mixture at the end. Okay, so you basically do not need to write about all of the entire process, but how you could obtain that dry sample of the mixture that is found at the end of the reaction. Now, this thing is important. End of the reaction, right? So yeah, simple. Filter, wash, leave on the filter paper to dry. As simple as that. So filtered the calcium phosphate, filter the crystals of calcium phosphate Ca3PO4 solid, right? Then wash it with distilled water, then wash it with distilled water, then wash the residue with distilled water, and you then dry the crystals on the what? On the filter paper. Then write on the case and then write on the filter paper and then write. You then write on the filter paper. Okay, so yeah, this basically brings us to the end of question 6.